Okay guys, so in this video we're going to be talking about dynamic programming, one of the most toughest parts in computer science. So it's something which is always dynamic changing. It has a lot of logic and a lot of mathematical aptitude which you're going to be needing to actually solve this type of problem. So let's go and take a look in actually. So the Floyd-Warshall algorithm is also used for in the pairing of solving the all pairs shortest path problem. So the problem is to find the shortest distances between a pair of vertices, between a pair of vertices in a given edge-weighted directed graph. So let's take a look at the components here. A pair of vertices in an edge-weighted directed graph. So a directed graph is basically when two different vertices, let's call this V1 and V2, are actually directed. So the direction is actually specified, and edge-weighted is basically the weights of the edge is specified. So it's finding the all pair shortest path problem. So the shortest path between vertices from, let's see, V3 and this is V4. So what's the shortest distance between, let's call this 7, 10, 2, and this would be 6. What would the shortest path between V1 to V4 be in this case? It would be obviously be this one. It would be 6. So you can see the shortest path. The Floyd-Warshall algorithm will help us in that. So the first thing is we're going to specify a graph here. So it would be 0. So you see the following graph actually represents a graph here. So let's note that the value of graph ij is 0 if I is equal to j. So the graph ij is infinite if there's no edge from vertex I and j. So for vertices I to j, if there's edge weight, it's 0, else it's infinite. So the output, let's go and take a look at how the output is actually deconstructed. So let's take a look at the algorithm now. So the first, we initialize the solution matrix same as the input graph matrix as the first stuff. Then we update the solution matrix by considering all vertices as intermediate vertices. So what would be intermediate vertices? Suppose we have this. I'm going to provide a simple example. What would be intermediate vertices? This would be the source. This would be the destination. So V2 and V3 would be considered the intermediate vertices. Okay, so you basically get it now. So the idea is to pick one by one, pick all the vertices and update all the shortest paths, which include the picked vertex, as the intermediate vertex in the shortest path. So this is confusing. Let's take a look at it again to make sure you understand it. So one by one, we're going to pick up all the vertices. So we have 4 different vertices, and we're going to update all the shortest paths, which include the picked vertex as the intermediate vertex in the shortest path. So when we pick a vertex k as an intermediate vertex, we already have vertices 0, 1, 2 to minus k as intermediate vertices. So for every possible ij and source of destination vertices respectively, there are 2 possible cases here. K is not an intermediate vertex in shortest path ij, so we keep the value of dist ij as it is. So k is an intermediate vertex from ij, and we update the dist ij, dist ik plus dist ij. So let me tell you what this means exactly. So we have v1 here, we got v2, we got v3, we got v4, and this is v5 I guess, and this is v6. We're going to stop it right there. So what would be an intermediate vertices? So we have I, which is 1, we have j, that is k, 4, sorry. So we want to go from v1 to v4. So we would go from, I would say, 2 to 1, this would be 3, 2, okay? So we would start with distance ij, that is 2, plus 2, plus 1, that is total of 1 to 4, that is equal to 5. So we would add each different vertex. Next, we would go from v5 to v6 as well to make sure we check it. And in this case, we have 3 plus 2. This is also 5. So the distance is the same, but why are we not selecting this? Obviously because we haven't reached the source destination. There's no link here. So that's what they're basically saying. So the following is the implementation of the algorithm. So let's take a look. First we have stdio.h, then we got 4 vertices like we talked about. And then we have infinite. So define infinite as a large number of values. So it can be 99999. It doesn't have to be infinity in most cases, since we don't have enough memory to actually store that. So we're going to have the print solution. The solution is going to be the distance. So it solves all pairs shortest path problem. So we have void Floyd-Warshall. So this will be our main function. So the distance will be the output matrix, and we'll have the shortest distances between every pair of vertices. So we have the distance VV, I, J, and K. So we initialize the solution matrix as the input graph matrix. Or we can say that the initial values of the shortest distances are based on shortest paths, considering no intermediate vertices. So they're just basically the intermediate or the input graph. So the solutions matrix is basically the input in the first step. Then we use two for loops and actually iterate to each possible vertices. And then we actually calculate the distance. So we actually go and initialize that. So what this means is we're just initializing the solution as the input graph. Okay, so now we add all the vertices one by one to the set of intermediate vertices. So before the start of iteration, we have the shortest distances between all the pairs of vertices, that is the input graph, such that the short distances consider only the vertices in set 0, 1, 2 to k minus 1 as intermediate vertices. So we have to go to k minus 1. We talked about why we should do this, why do we select 4 instead of 5, 6 in the example 1, 2, 3. Why do we do that? Because they were k minus 1. So that's what it's saying. So at the end of the iteration, vertex number k is added to the set of intermediate vertices, and it becomes 0, 1, 2, k. So in this case, what would be the intermediate vertices for 3? It would be 1, 2, where 2 is actually equal to k minus 1. And k would be actually equal to 3. You get it? So I think you now understand what I'm trying to say here. So actually, for every k two vertices, we're going to actually pick the vertex as a source one by one, and we're going to pick all the vertices in the destination. So for j less than the number of vertices, we would say as we picked up each vertices, now we're going to have to go and calculate the distance. So if the distance of ik plus k of j is less than ij, then we update it, else we don't, since we want the minimum. Okay, so we're going to print out the shortest distance, and there it is. So now we have to provide the utility function. So the utility function is actually the area which actually helps us calculate the distance here now. So we have the print solution utility. So we're going to print the following matrix shows the shortest distance between every pair. So if you just want the source and destination, that would be fine, but for every pair, we're going to have to do it differently. So you have two for loops for ij, and then we have all these are infinite. We talked about how these are infinity, and it's 0 for the base case. And then we're going to print this. Also, we're going to just print out the values of dij. In most cases, if dij is given, if the distance is actually given in the input graph, we're going to print out that, or we're going to add infinity. So we're just having the main function here. It's simple as that. This is the basic graph. This is the input graph which I'm talking about. This is the first thing which we're going to be considering as a solution. And then we're going to be using the Floyd-Warshall graph algorithm to actually go and do that. So the output is actually, we talked about how 0 is being the normal case for the distance, and how infinity is actually occupying all these cases. So this is the shortest base distance. So let me tell you what this actually means. So this is basically, since we have 4 vertices, it's actually 0, 1, 2, and 3. And this is actually 0, 1, 0, 1, 2, and 3. So you can see the distance between 0 and 0 is 0, 1 and 1 is 0, 2 and 2 is 0, 3 and 3 is 0. And 3 and 0, since this is a directed graph, that means 0 to 3 gives us 9, but there's no graph or no pointer going from 3 to 0. That means it's infinite. There's no valid graph. So that's why we mark this as infinity. So you can see what I'm saying here. So the time complexity for the Floyd-Warshall is huge. Why? Because we have three for loops. We have for I less than v, we got j less than v, we got k less than v. So it's such a headache. We're going to have to do 3 times. So that's the basic time complexity here. The above program only prints the shortest distances. We can modify the solution to print the shortest paths, also by storing the predecessor information in the separate 2D matrix. So this is going to be quite complicated. Maybe we can do that in another lecture, I guess. So also the infinite value can be taken as int max with limits from h. So that's why we have the limits from 2 power 32 minus 1 or 2 power 31 minus 1 in this case. So this is the basic collection. We don't want it to go to an overflow, so that we don't want to take it literally as infinity. So you can actually see how this is actually modified. This is the basic algorithm which you should remember for this case. So we have defined, we got limits, This is a base case. If ik is not equal infinite and k is not equal infinite, then if this is less, we want to print out this one. This is the main algorithm. So if you remember this point correctly in summary, then you are good to go. There you go, guys. I hope you learned about Floyd-Warshall algorithm in complete detail. So I'll see you in the next video. So guys, let's take a look at greedy algorithms. We talked about MST and premise algorithms and most. So I'm going to be skipping in most of these parts, which you already reviewed, and go straight to the greedy algorithm phase. Let's go and do that. So we're going to be looking at Dijkstra's algorithm, and one of the most famous algorithms in terms of finding the minimum spanning tree. So let's go and take a look at that. We maintain two sets. One contains the vertices. One contains the vertices in the shortest path. Another includes the vertices which are not yet visited. Same as prims, except at the step of the algorithm, we find the vertex which is the other set and has the minimum distance from the source. So I want to show this in an example. Explaining this won't actually make you understand. Let's go and take a look. Okay guys, so let's take a look. This is a very important and one of my most favorite algorithms of all time. So let's take a look. We start off at 0. So like I said, in MST, 0 is added and we have all these as 0 and we get all the others as infinite. But before that, we want to make sure which has the lowest distance. So we consider this. What is connected to 0? It's 1 and it's 7. So when 1 and 7 is actually connected to 0, what does that mean? This has the lowest distance. So what does that mean? We should go to 1. Simple as that. So we'll go to 1. So what does this mean in MST? It has 0 and 1 in this case. Let's keep continuing. So the sets of 0 are all marked as infinity like same before. So we include 0 in the set. And then we have the vertex of 1 at 7. But instead of 1, 7, we took the one which is the lowest of distance. That's what we consider 1. So like this in the previous example, 1 is picked since we have the lowest distance. That's what the slides are telling you. So now we consider the next distance. What is next to 1? It is the vertex of 2. But what is the distance between 1 and 2? It's 8. But are there any paths and adjacent vertices from 1? No, there isn't. It's only 2. So what does it give us? We are left with no choice except to go to 2. You can see here what I'm talking about. So what does that mean? This is basically 8. This is basically 4. So to go to 1, it took 4 points, and then to go to 2, it took 8. So a total distance of 12, which is marked over there. So now what does this happen? So now what happens? Think of it. So this is 12, and this is 8, which is lower, which is better, which is more optimal. This, of course, since we may be thinking this may be giving us a better spanning distance. So hence, we go from 0, 1, and 7. We don't go to 2 because of the distance. So this has a lower distance rate. Which is lower? 8 or 12? 8. So that's why we add 7 here. Then we took a look at the vertices of 7, which are the vertices of 6 and 8. So let's take a distance and compare that now. So we have 7 here. So in 7, let's take a look at what actually happens here. So we have 2 vertices, we got 6 and 8. What happens to the distances? So we have 15 on one side and we have 9 on the other side. So what does that mean? We go to 6, obviously, since 12, 15, and 9, which is lower? 9. So we add 6 into the MST. So you can see here what I'm talking about. So now let's take a 6. We have 2 more, 15 and 11. What does this mean? So we can take any 2 paths, but since this is lower, we're going to take 5. Done. So we add 5 into the MST. Next, after we add 5, we take a look at what is the only remaining option, that is 4, so we add 4 into the MST. But guess what? With 21 points, we just lost all the things which are actually necessary. We still need to cover 2, 8, and 3. So where does the remaining points come from? So this is where we actually cut the line from here. So instead of going from 11 to 21, we take a look at the next preceding step, that is 12. So we go to 12, we take the distance, we go to 2, we visit 2 and go to 8 since it's 14. 14 is still less than 21. Then we go to 3, it's still less than 19. So what's the remaining point here? 21. So the following MST would be 0, it goes to 1, then it comes back to 7, then it goes to 9, then it goes to 6, then it goes to 5, then it comes back and goes to 2, then it goes to 8, then it goes to 3, and it comes back last at 4. So that would be that mistake. So the implementation, it's basically the same. Let's take a look at what actually changed here. So we're going to use a Boolean set of special set to represent the set of vertices include the SPT. And we're going to use the SPT set V is true to whether it's located yes or not. So let's take a look. We have the basic V, except in this case we're using 9 different vertices. Then we use the minimum distance. So minimum distance has the distance value and it has the bool special set to locate whether it's true or not, whether the vertex is in the SPT or not. So we have the int minimum value as same as before in prims, except this one's going to change. So let's take a look. And before we had a different condition in prims, now we also have a different condition here. So the SPTs were false and minimum distance less than min. So it's the same thing, but different parameters have changed here. Before it was a different parameter, now we're using the distance value here. Before it was actually the edge weights, if you remember correctly. So now let's consider this. We have the inprint solution, a util function to construct a distance array. So we have the distance and the number of n. So we use the number of vertices as the maximum number output for this for loop and actually specify each number distance to make sure we get the distance from the source. Then we're going to use a function that actually implements the Dijkstra single shortest path algorithm, which is known as SPT. So in the single shortest path algorithm, we use the agency matrix representation. So to get that, we're going to use the graph and we're going to use the source, nothing else in these two parameters. So we're going to have the distance v, the same thing, we're going to have the bool sp set. So the output array, distance I will be holding the shortest distance from source to I. And we have the SPT, will hold true if the vertex is yes present or not. So rest implies all the distances to infinity except the vertex which is first, which is now going to 0. So that's what it basically did. And the distance y is int max is infinity, and SPT is false. Then we enter source 0, like I said before, right there. We're going to find the shortest path now. Let's take a look. So we're going to use the count function and actually use the vertex v minus 1. Why is it v minus 1? Well, we already took a look at 0 and matched the first vertex of v1 to 0. So what does that give us? We cancel out one vertex, that is v minus 1 now. So we're going to pick the minimum distance vertex from the set of vertices not yet processed, that is not in SPT. So the SPT of the vertex should be false. That's what it's basically saying here. So and u is always equal to the source in the first iteration. So u is the minimum distance from distance to SPT set, since u and v is the minimum distance here. So we're going to mark SPT of u is true. We're going to make sure that's true. And we're going to make sure we get all the edges and vertices of the picked vertex. Why do we need to get the edges and vertex? Take a look at this. If you remember from a previous example, this was, I guess, 8. I don't remember the number. It was 1, I guess. Okay, let's just give it as 2. Then we have 3 here, and we got 4 here. So this has a distance of 4, this has a distance of 3, and this is 2. What would you select? So the total distance of here would be 4, total distance would be 6, total distance would be 7. It would be 3, obviously. So it would go from 3, 2, and 3. How do we decide between 3 and 4? Well, it's actually between the minimum distance, which we're doing right over here. So let's take a look. So we update distance v only if it's not in the special set. That means we don't want to repeat it again. So there's an edge from u to v. The total weight from source v to u is smaller than the current distance. We want to make sure it's smaller than the current distance. If it's not, we're not going to be utilizing it. So that's what we actually said over here. That's what I explained here. So first, let's take a look at this if condition. It's looking quite harsh, but let's deconstruct it. First, it should not be in the set, and it should be in the graph. Then the distance should not be equal to infinity, and the distance plus distance of u plus the graph of v should be less than the total versus distance. So this is the most important point, I guess, of the whole graph structure. Just remember that. And if that's true, then we add this. Then we add distance. Then we add dist v is equal to dist u plus the graph of u and v. We just want to make sure that it is minimum. If it is minimum, then we're just going to make it that. Then we're going to just print out the solution. We just want to construct the distance array. So we have the main, as simple as before. We just have to add the graphs here. So this is just basically adjacency matrix stating which is which and which is that. So that would be basically 1. Let me just make it easy. 1, 0, 1, 2, 3, 4, 5, 6, 7. It would be 1, 2, 3, 4, 5, 6, 7, 8. So this would be given by this. It would be 0, 4, 0, 0, 0, 0, 8, 0. So what does that mean? So 1 is connected to 2 and a distance of 4. So that's how you basically get it. So we just constructed this example right over here, that we had to register a graph of 0. 0 is the total distance here. So the output, we can have the distance, and this is from source, and we get the nodes here. Let's take a look here. The code calculates the shortest distance, but doesn't calculate the path information. We have the shortest distance, but we don't have the path. We specify the path being in the whole of the SPT being a good set. 0, I don't remember correctly, it was 0, 1, 2, 7, 6, 8. It was something, but I did remember the last is 4. So we can create the parent array, update the parent array when distance is updated, and use the shortest path from sources of different vertices. So what it's saying is we use the parent array to actually construct the shortest path and shortest distance path here. So the code is for an undirected graph. So the same Dijkstra function can be used for directed graphs as also. So a directed graph is something which is pointing to another area like this. An undirected graph is something which just connects. So 2 can go to 1, 1 could do 2, it doesn't really matter. So the code finds the shortest distance. If we're interested only in the shortest distance from the source to a single target, we can break the for loop and pick the minimum distance which is equal to the target. So what this actually means is, so we actually calculate the distance from each and every single point to make sure that we get all the cases. If we don't want that, if we want to have only one and the last vertex, I don't remember these vertices, there was something, this was something. It was something like this. It was something like this, where this is 0, this is 1. Yeah, I don't remember. So if you only want to calculate from 0 to 4, we would just make sure that we remove the for loop for all the different iterations and make sure that target value is only equal to 4. So that's what this is saying here. So the time complexity is just the same as prims. It is O of E square. For an instance list which you used as before, it will be O of E log V, where V is the number of vertices and E is the number of edges. So that's it, guys. I'll see you in the next video. Before, I do have one more point. So the Dijkstra solver doesn't work for graphs with negative edge weights. For graphs with negative edge weights, you should use Belfort algorithm, which we'll be talking about in a new video. You can check out the link in the description below. I'll see you soon. Okay guys, so in this video, we're going to be learning about breadth first traversal, or BFS, for a graph. So let's get started. So breadth first traversal for a graph is similar to breadth first traversal for a tree. So let's consider this. So we talked about trees before, having these similar structures. Now the only catch is, unlike trees, graphs may contain cycles. So we may come up to the same node again. So a graph is something like this. So you can see the difference. In the tree, once we go down, we may not be actually coming up. But see here, you get the form of cycle. So that's what they're trying to say. So to avoid processing a node more than once, we use the Boolean visited array. So we use a bool which is true or false. We have an array. So we have an array of booleans for each node. So if it's true, that means we visited it. If it's false, that means we didn't. For example, in the starting node, you have the travel vertex of 2. So when we come up to vertex 0, we look for all adjacent vertices of it. So 2 is also an adjacent vertex of 0. So based on what they said, that's what you're basically going to get. So if you don't mark visited vertices, then 2 will be processed again and it will become non-terminating process. So let's draw this diagram here. Let's see what they're trying to say. Okay, so first it starts with 0. Then it goes to 2, then it goes to 3, then it goes to 1, then it comes back to 0, and then it has to come back to 2. But we're going to stop it right over here. So we terminate it using the bool. So by using the bool, we only visit each node once. So you can see what I'm trying to explain in this basic diagram here. So the C++ implementation is quite easy. Let's go through it. So we have the iOS node stream, we have the list, which is used for the array, Then we have using names for the STD, the basic converter. Then the class represents our direct graph. So let's go. So we have class graph. So in the basic graph, we have the basic components. We talked about those. We have int v for the number of vertices. Then we have list int adjacent. We talked about the adjacent nodes for 0 having 2. This is the adjacent node. We talked about that. And this is actually the data structure which implements that. So it's basically list, the type of the data, and the name of the array. So now we have public graph int v. So this is the constructor which we're going to be using for building the graph. So graph int v. Next we have the function void add edge. So add edge. So this is the vertex in which we're going to be adding, and this is the edge in which we're going to be adding it to. So that means if we're going to add an edge, say, let's take the basic example which we've always been using. So in this example, we're going to be adding an edge from 2 to 1. So we're going to say 2, 1. So that's what we're going to be doing here. Then we have void BFS. This is the basic function which also calls the BFS function. So we're going to be defining that later. We're just constructing it here. Then we have graph int v. This is where we actually define the v. So this.v is a v. We're constructing this as this element. Then we're using adjacent as a new list of int of v. So we're creating an instance of adjacent using this v structure. Next, we have void graph add edge. So we talked about edge being pushed back. So we have the adjacent of v, that is adjacent of 2 in this case, dot push back. That's w. So w is added to v's list, so we have 1. So what that means is we're connecting 2 to 1. So it's being connected, a new edge is being formed. So now we have BFS. We're going to have to mark out each bool. First we consider the bool. So bool visited is equal to bool of v. Then we're going to have to say if each one is visited or not. So first, initially, since none of them are visited, we're going to have all of them as false. Then we're going to go to each queue. Then we're going to say visit of s is equal to true for each queue visited. And then we're going to push back that particular vertex. Now, let's see this. We have the iterator of I. So we're going to use this iterator to actually decide whether and actually iterate through each of the elements which are queued. So while q does not equal to empty, so while it's not empty, we're going to be actually dequeuing the element from the front. So in a queue, let me just draw a basic example. We have the following like this, and this is, so we have the front, then we have the rear, and then the elements get added like this, and they keep going separately. If I add 0 here, 0 goes here, 0 goes here, 0 here, and it finally comes out here. And it just keeps it's like a basic queue. You can see a line, for example, a line. If we're waiting in line for someone, so we have 1, 2, 3, 4, 5 people. So 1 goes out to the checking order, then 2 comes in here, then below 5, 6 may come in. So it's basically like that. So we can queue that pop front. So we're basically actually popping the front of the queue. So we're also now going to each adjacent vertex and whether saying if it's queued or not queued. So we're going to get all the adjacent vertices of the dequeued. And then if vertex x, if the adjacent has not been visited, then it is marked visited and then queued. So let's see what this says. So let's take a look at the for loop. So for I is equal to adjacent s dot begin, so we're beginning, and wait does not equal to adjacent s dot end. So while it does not equal to end and it begins from the start, what we're going to do is we're going to be if does not visit a I. So if we have a different layer network here, and if it's saying we do not visit this path of I, then we're going to be visiting it. Suppose we just visited these two segments and actually led us to the end. If this is something new, we haven't visited it before. This is a new edge, like we talked about in 0, 2, 3, 1. So this is a new edge which we didn't talk about before. Since this is a new edge, we're going to be visiting that. And we're going to be pushing back this edge here. So that's what it basically says. So you can see we're basically using the int main, and we're just giving out the class main using the edges. We're creating the edges. We're doing the graph. So graph of 4 vertices, 1, 2, 3, 4, I guess. And we're creating the edges here. So we have, it's 0, 1, 2, 3. So we have 0, 1, 2, 3. So we have 0, 1, then we have 0, 2, then we have 1, 2, then we have 2, 0, then we have 2, 3, then we have 3 and 3. Great. Let me just mark these up. 1, 2, 2, 0, 2, 3. Perfect. There we go. That's our graph. If you can mark that in. So we just basically add to the BFS of 2 here, the vertex of 2. So the output is basically from the graph. Let's go back if we can. Since we can, let me just draw the graph what we did over here. I believe it's something like this. Yeah, it's something like this. Yeah, I think that's how it says. So it starts from 2, it goes to 0, then it goes to 3. Since 3 is the one which is beside 2, we're going to have to go back in 3. Then last, since this is the terminating point, we go to 1. So that's how it's actually done. You can check out the illustration. Let me just actually show it to you guys. So note that the above code traverses each vertex reachable from a given source vertex. So all vertices may be reachable for a given vertex at least. So to print all the vertices, the BFS function is going to be used. We talked about that, the time complexity. This is a good area. So it's O of V plus E. So V is the vertex, and E is the edge in which it actually transverses from. So it has to go to each vertex and edge, so it has to cover all the cases. That's why it's O of V plus E. So let me give you a good demonstration of how this actually caused. So guys, listen up, let's do this. So we have a graph here, 1, 2, 3, connected like that, 4, 5, keeping it simple. Great. So now we're going to have to do the BFS for this. So the BFS would be, if we start at 1, 1 can go to 2 or 3. So we're going to go from 2, and then we have to come back and go to the next one which is adjacent to this. That is 3. Then we start from 2. So what is adjacent to 2? It's 4. Then we go back to 3. And what is adjacent to 3? That is 5. Then since 6 is the only remaining part, it would be intuitive to just get 6. So that's the basic BFS for this case. So we also talked about another example. Let's go to that as well. Welcome back, guys. So in this video, we're going to be doing the depth first transversal or DFS. This is probably one of the most important algorithms, so I highly suggest you listen carefully. So the depth first transversal is for a graph, is similar for a depth first transversal for a tree. So the only catch here is, unlike trees, graphs may contain cycles. So you may contain the same node once again, so it's a repeating cycle. To avoid processing a node more than once, we use a Boolean visited array. Let me just mark that. So this is important. A Boolean visited array makes sure that we don't do the same thing twice. So for example, in the following graph, we start a transversal from 2, and then we move on to 0, and then we look for adjacent vertices of 2. So if 2 is also adjacent of 0, so we move on to the following direction. So if you don't mark visited vertices, then 2 will be processed again. So this will be a non-terminating process. So let's take a look for the following example. So we have 0 here, we got 2, we got 1, and we got 3. So in this following example, which I just stated here, just mark that done. So we start at 2, we move on to 0, so 2, 0. Then since what else is near 0, you can't go back to 2, it will go back to 1. So you go to 1. So now what happens? All these things are filled. So the depth-wise transversal is filled. So it goes back to 2 and moves on to the next direction. So that would be 3. That's how it's done. So you can see the example here which I provided, the same different thing example, and actually moves on to the following direction. So let's go and implement this using the DFS in C++. So we have the following ISO stream, the list, include US namespace.std, simple as that. Then we're going to use a graph. We're going to be initializing using a v, the pointer, the list, int, adjacent. It's going to give us a vector here. So we're going to have to use the function this. We're going to use void DFS util, and then we're going to use int v for the vertices and the bool visited. I told you visited is whether true or false. So we have the graph, public constructor, we have the void add edge, we got the DFS for this, which is int v. So we have int v. This is the basic same for BFS. For DFS, or anytime you increase a graph inside a computation, this is the basic thing which we're going to be using. This is the same thing we're going to be using. We're just connecting W to V to W, where this is one vector, this one vertex, and this one vertex. We're going to be connecting W to V back again. So next, we have graph. So let's see how we actually implement this. So first is we're going to be visiting the first node which you want, of V, since V is the starting node, as true. Then we're going to go to the iterator I. So we created a new iterator in the vector int, and we're giving it a name of iterator of I. So in iterator of I, this is where the magic happens. So we're going to start at the adjacent V to begin, and we're going to move on to adjacent V of ending. So we're going to go to each different I which is located and adjacent to the vertex of V. So we talked about the example how 2 had 1 and 0 as adjacent. So we're going to move to 1 and 0 in this case. This is a basic example. So it does not visited of I, then we're going to use this following condition here. But this is the vertex. Then we can do the DFS transfer for vertices reachable from V. So if we use recursive util, then this would be the following. We have ds of int V. We're going to mark visited of new bool of V. Then we have for each different for loop, we're going to mark it as false at the beginning. And then we're going to call the recursive helper. So that would be basically DFS util V comma visited. We'll be going to each different vertex in a following recursive function. So you can see here we just added a few edges here, and we just considered this. So let me just construct that. So this is basically 0 to 1 and 1 to 0. So this is the same example which we did before. And we will get the following output. So let's look at an undirected graph. So this is interesting. Let's take a look. So let's go through it. How do you handle a disconnected graph? So the above code transfers is only vertices reachable from a given source. So these vertices may not be reachable for a given vertex. So let's go and see how we actually go and implement that. So to complete a DFS transversal for such graphs, we must call DFS util for every vertex. So by calling DFS util for every vertex, we should check if it is already printed by some other call DFS util. So we don't want to make sure that we don't repeat the vertex again and again. So the following implementation does this. Let's go and see how it goes. So we have the basic ISO stream graph like we discussed before. Same thing. Let's take a look at what's different. So you have the F constructor, same thing before. Push back, same thing. We got the same thing as before. But the thing which changes is this. So let's take a look at what actually changed here. So to do a BFS travel, first we do is we created a new visited of V. Then we make it all false. So this is the same as before. So now we're going to call the recursive helper function and print DFS transversal starting from all vertices one by one. So this is what's going to be changed. So we're going to use a for loop. We're going to be marked it as false, and we're going to do a DFS for all visited of I. So that's the thing we changed. So everything else is basically the same here. We get the following output. So this is for an undirected graph. So thanks guys for watching. For the time call basically, let's go and review that. Hey there guys, and welcome to this lecture. So we're going to be talking about the bridges in a graph. So let's get straight to it. So guys, an edge in an undirected connected, so these two are important, connected graph is a bridge. If you're removing it, disconnects the other graph. So for a disconnected undirected graph, definition is similar. A bridge is an edge, removing it from which increases the number of connected components. For example, let's take an example here. So if you have 4 different, let's see, nodes here. We got 1 node here, and let's say we got 3 different nodes here. So can you guys guess what would be a bridge in this case? It's definitely this here. So if we cut this edge, guess what happens? Let's go and remove it. So we cut that edge right over there. So what just happened here? So these two are now 2 separate graphs. So anything which actually separates the graphs is actually an edge or a bridge in this case. For example, if I cut this, it doesn't get separated since the nodes are still connected, so it wouldn't be a bridge. So in this case, this here would be the bridge, this segment over here. So like articulation points, bridges represent vulnerabilities in a connected network and are useful for designing reliable networks. For example, in a wide computer network, an articulation point indicates the critical computers and bridge indicates the critical wires or connections. So following up some example graphs with bridges highlighted in red color. So let's consider this. We have the following graph here, and in this case, the bridges are, sorry about that. Yeah, the bridges are 0, 3, and 3, 4. We talked about why these are connected edges. Since if we remove these two, what happens is you completely break off the graph. Same thing with this. If I remove this point here, 6 and all these components get separated. So we would get this as one component and all of this as another whole component. The same things for this. For this linear one, we can just cut them like that. So to find all the bridges in a grid and graph, a simple approach is by one removing all the edges and see if the removal of an edge causes a disconnected graph. So let's try a few examples here. So for every edge u, v, do the following. Remove u and v from the graph. Step number 1. See if the graph remains connected. We can either use BFS or DFS. It's our choice. Then we add u and v back to the graph. So the time complexity of this method is basically, since we're removing each edge and we're adding it back, we're going to be multiplying the edge into v plus c. So that would be O of v into v plus c. Why? Since we're multiplying and getting back each edge. So that's why you have to consider this case. An OV algorithm is to find all the bridges like we talked about. And since the idea is similar to the OV algorithm in articulation points, we do a DFS raffle in the given graph. So a DFS and edge u, v is a bridge if there does not exit any other alternative to reach u or ancestor from u from the subroot of v. Suppose let's take the previous example here. So we have 4 linear points here. So we wanted 1, 2, 3, and 4. So if we want to get to 1, if there's no other point in which, if I remove this edge right over here, if there's no other way for 4 to reach 1, then that's an articulation point, or that's where you can actually cut the subroot. But suppose there is. Let's just suppose there is another way. So if I cut that, this nothing changes since it's just disconnected. So it wouldn't be a bridge. So as discussed in the previous proofs, the value of lower v indicates the earliest visited vertex reachable from the subtree rooted with v. So a condition for the edge uv to be a bridge is low of v greater than disconnection of u. So let's take a look at this. Let's read it once more to get a better understanding here. So the value of lower v indicates the earliest visited vertex reachable from the subtree rooted with v. So it's basically, in the linear example, that would be 1, 2, 3, and 4. Let's take a look here. If the lower v would be basically, since we cannot reach 2 and 3, let's say for example we're going to have to reach 1. So what's the earliest visited vertex reachable from subroot of 3? It's basically 3. So 3 would be the lower v, and that would be discussion view in this case. So take a look at the implementation. So we have IOStream, we got list. For actually calculating the list, we got nil is equal to -1. We have namespace SD as basic. Then we're going to have the class graph. The basic graphs we have int v. You got the adjacent list. So this is interesting. We have the void bridge. The bridge has int v of the number of vertices visited to make sure we visit each array. The description element. You got the low element. And we got the parent. So we got the public class, and we got the graph generator, we got the edge generator, and we got the bridge generator. So 3 generator constructors here. The constructor for the graph, where v is the vertices, edge, 2 vertices, we got the bridge. So in this case, for the graph of v, so this of v is equal to v. So we got adjacent is equal to new list. So we can say we just added a new v element vertex to this list over here in this case. So we have the graph v, we're just pushing it back, and we're connecting the adjacent, the 2 vertices of v and w. So we're pushing back w, and we're connecting an edge from v to w, and from w to v. So let's take a look at the DFS transversal. So a recursive function that prints out and bridges together using DFS. So u, the vertex to be visited next, and visited, we keep tracks of the visited. We got description, discovery times, it stores the discovery times of the visited vertices. Then we got the parent. So it stores the parent vertices here. So let's take a look at the graph here. So in the graph, we got the bridge. So we got visited u, we talked about why so. So we're putting a static in time for simplicity. So we're going to avoid using the static variable by passing a pointer. So if you're not taking a pointer, pointer is actually something which actually addresses it to a memory block. So instead of saying a particular location, we're actually specifying the memory location here. So if you want to find out more about pointers, you can check out another lecture which I explained before. So that's something which is quite intensive, specified only for pointers. So let's mark the node as visited, and then we're going to be saying visit of u is equal to true, since we did visit that. So, and the discovery u and the load time of u, we're going to be adding a plus time. So we're just incorporating the time and just assigning them to the values there. So initially, the discovery time and low value are both equal. So let's go to the vertex adjacent to this. So we have the iterator of I to help us with this case, and we move on to I. So for I is equal to adjacent of u dot begin, and it doesn't equal to n, and we're going to be using BFS or DFS here. So we're not going to be specifying BFS in this example, we're going to be using DFS. So DFS is much more better since it provides a depth-wise Floyd-Warshall, and which will be useful for us if actually when we're considering that we're going to be moving and searching along bridges in this case. So we would say int of v is equal to point of I. So it gives us the current location of the iterator of I. Remember, I is the iterator. So this means if v is not yet visited, then if does not visit a v, then it goes and visits v. So parent of v is u. So let me tell you why. So u is connected to v. So the parent of v is obviously equal to u in this case. So we have the bridge util. So this is something which we did not see. So we talked about this. We have the disk, low, and visited. So we got the v, the first vertex. We got visited whether it's true or false, etc. So we're going to say the low of u is equal to the minimum of low of u and low of v. So in this case, we can say the low of u and low of v are basically the lowest discovery times in this case. So if the lowest vertex reachable from the subtree in this case is v, then we're going to be using u minus v, since we want the difference. So in the bridge, we're comparing low of v. If greater than discovery of u, then this is the most important point here. So we're going to use this if case we talked about, where we talked about how low of v, if greater than discovery of u, we're going to be printing out u and v, since that is the most important case. So if you forget anything about this whole lecture, just remember this one simple point. So update lower value of parent function, else. If v does not equal to parent of u, so else if v does not equal to the parent of u, so as long as the parent of v is not the parent of u, we're going to say the low of u is equal to minimum of low of u and discovery of v. So this is another important case, another case over here. So we just want to make sure that we test for it for the preceding case. We just want to consider the contradiction here. So that's where we considered this case. So now the DFS phase function is to find all the bridges. Now let's use a recursive function to actually go in to each part. So we have function bridge util, and you've got void graph bridge. So let's take a look at this. So we're just connecting the bridge here. So bool visited, no bool of v, we're checking if it's visited or not. And now for int discovery is equal to new v, and low we're going to be intersecting with the first vertex, and parent is the same. So initially these three are the same. Next, we're going to initialize the parent and visited arrays. So parent of I is equal to nil, and we have the visited of I is equal to false, since we did not visit it yet. And we're also specifying for each different parameter, we're specifying the parent to be nil, since we're not going to be assigning a parent depending on how we transverse this graph. So let's call the recursive helper function to find the bridges. So in DFS, we rooted with vertex I. We're going to say that we did this. We're just going to specify all the functions which we learned until now. So now we're just specifying the main function. We just created the main. So we're just printing out a graph. So we create a graph. We connect the edges. You can see we connected another edge over here. So we have for our, let's see, 0 to 1. Then we can recreate the graph. So we end this. Now you can see the output here. So let's take a look at how they're actually connected to this graph. So for the time complexity. So the above function is a simple DFS with two different additional arrays. So we have a DFS is O of B plus C. So for each list. So the above function, the time complex is same as DFS, which is O of V plus C for instance list, representation of graph, that is in the simplest case. So that is it, guys, for bridges and articulation points. We'll be looking at the next part. We'll be talking about more functions and more problems. I'll see you then.